Click record. So we are going to learn more about the idea of estimation today. So we were learning about testing hypotheses for the past couple chapters. This is chapter 13 now, but we know how to formulate ideas and questions. We know how to ask them. We know how to come up with statistics that will measure those things and make simulations to test our hypotheses and see if they're good or not. We can find a p-value. How likely is our null hypothesis model to predict things just happening due to chance? And we can calculate how likely that is predicting the weird thing that we saw that happened that we're asking our question about. All right, so we've done all that, and now it's time to get a little bit more precise. So this is chapter 13. There's a lot of very important things to talk about. The biggest one is confidence intervals. We'll get to that towards the very end. And that's actually the last piece of information that you need for project 2. So I would like to schedule project 2. I think I like to give you guys like 3 weeks to do a project. So remember, obviously Canvas is down right now. I gave you project 2 zip file on Discord, so you're able to get started on it. It's a cool one, just like project 1. And my goal is to have it due. Let's do the Wednesday 3 weeks from now. So November 5th, I think that's my goal. That seems like a decent due date for that project. So due November 5th, because we'll need the end of these slides to get them, and I think that will be perfect. So yeah, that's 3 weeks, right? Did I do that right? 1, 2... Oh, no, I'm sorry. 1, 2, 3, 12th. November 12th. 1, 2, 3 weeks and 2 days. That should be plenty of time. Okay? So, yeah, it takes this chapter to do it, but you can do about half of it right now, and then you'll be able to complete the rest once we're done on Wednesday, I believe. So, yeah, let me know if you have any questions about that. You have it on Discord. I've written a note for myself to release it to us once Canvas comes back online. Should be today, I think. So yeah, let's get started with a concept that you may have seen before, like when you took standardized tests. Like, did you take? I assume there's still some form of standardized test that you take in high school, right? To like see where you are, and then you get in the mail, or you take the SAT or something. You get it back in the mail, like what percentile you scored in. We've seen that word before. So all that's important to us now. The pth percentile is like a number, like the 10th percentile. Then you're in the 90th percentile. It just means this. So like if you're in the 10th percentile, that's not a good thing. That's like you have scored as good as or worse. You have scored as good as 10% of the people. There's 90% of the people above you. That's kind of what that means. All right, so that's the 10th percentile. So you want to be in the 90th percentile. You want to be as good as people. You want to be as good as or better than 90% of people. So that's what it means. The pth percentile of a bunch of values. This is a little wordy. It's the smallest value in that sequence, in that collection, that is at least as large as p% of the values. So if you're in the 10th percentile, that means you're at least as large as 10% of the values. If you're in the 90th percentile, you're at least as large as 90% of the values. There's only like 10% of things above you, all right? So there are a bunch of competing algorithms to find the percentile. We get a nice fancy function thanks to our library, but to find the pth percentile of something, the way that your book has explained it is the way that I'm going to teach it. So they call it the nearest rank method. It's the easiest one, which is nice. So what you're going to do is you got a bunch of numbers. You want to find like the 90th percentile of it. You're going to sort them. You've got this many of them. You got n of them. Let's say you've got n numbers, where n is like, I guess, 5. That's going to be my example. There's 5 numbers, and you want like the 90th percentile of n, of 5. So you're going to calculate 90 over 100 times n. So that's what you're going to do. Like, take that percentage of the number of things you have in your sequence after you've sorted them, and call that number that you get back k. We're going to do an example in a second. That is telling you, like if it's a whole number already, then it's that number. Take the kth element of the sequence, and that is your pth percentile. So if you want to deal with indices, remember the indices start at 0, so like the first thing is really the 0th thing. So you got to subtract 1 if you want to use indices. Otherwise, you round up and go to that that element. All right, that's what you do. So let's calculate the 70th percentile of this sequence. It's okay if there were duplicates, by the way. You just got to sort it first. The 70th percentile of this one is going to be 12, and I'll show you why in just a second. All right, so I've got 5 elements. I want the 70th percentile. I want to find the number that is at least as large as 70% of the values. All right, that's my goal right now. So n, for this example, right here, my n is 1, 2, 3, 4, 5 things. And I want to find the 70th percentile. So what I'm going to do is I'm going to take 75 over 100 times my n. Times my n. So it's 3/4 of 5, which is, I don't know. But we can ask Jupiter, because Python, bless you, because Python can do math for us. Percentiles. So I can do 3/4 or just 75 over 100, whatever I want, times my n, which is 5, and I get 3.75. So if that's not a whole number, right? So it's kind of in between places. If there was an index called if there was a 3.75th number, that's the one I'd pick right now. That would be the 75th percentile, but it's not quite. So what I'm going to do is I'm going to round up to 4. All right, so it's 3.75. I'm going to round up to 4. I want the 4th element of my sequence. Does that make sense? That's how I do it. So it's 1, 2, 3, 4. If you want to do with indices, it's index 3. All right, that's the difference. So if you want to go to an index, it's 0, 1, 2, 3, or 1, 2, 3, 4. It's going to be that one. Does that make sense? And if you think about it, that's very clear because, like, all right, if it was 9, how many numbers are smaller than or equal to 9 out of this sequence? 3 out of 5 of them, right? What is 3 out of 5? No, go back. What has happened? Oh, goodness. I turned it into not code anymore. What's 3 out of 5 of them? That's only 0.6. That's only 60% of them, right? That would be 9. Does that make sense? That 9 is bigger than or equal to, it's at least as large as 60% of the numbers because it's 3 out of 5 things. 3 out of 5 things is at least as large as 3 out of 5 of those numbers, 60% of them. 12, though. 12 is the 4th element, so it's as big as, right, 4 out of 5 of the elements. What is 4/5? That's 0.8. So in addition to being the 70th percentile, it's also the 80th percentile. Does that make sense? So it could be a bunch of those numbers. It's just like you got to cut it off somewhere. You want the number that's at least as large as that many percentage of values, the smallest number that works for. It doesn't work for 9 because 9 is at least as large as only 60% of the values. 12 is at least as large as 80% of the values. So percentile 61 through 80 is 12. Does that make sense to us? So it can share a bunch of different numbers. It's also the 80th percentile. You can calculate that exactly if you want. It's like 80 over 100 times 5. What is that? That is 4/5 times 5, so it's also the 4th element. Index 3. All right, anything bigger then would be 17. 17 would then be the 81st percentile. Does that make sense to us? It's an interesting idea. So that's how you calculate percentiles. You do that. And so I want you to try. All right, why not? Here's the process. Make sure that the numbers are sorted. Cannot do anything unless they're sorted because you care about order. But there's your process. I would like you to please, if you can, find the 30th percentile of these guys. And maybe we can do the rest of these together, but like also give a head start if you want. But just do the 30th percentile of this list of numbers, please, using this, it's called nearest rank method to find them. All right, so just do this first one, please. And we'll come back, we'll see what the answer is, and then maybe we can try the other ones too. Okay, questions about the question? So 30th percentile of that group of numbers. What is it? You want the number that is at least as large as 30% of the numbers. And so you can play the game of doing the calculations, but you can also just do the formula. Whatever could it be? do the math, and then I'll show you the function that's in the data science. Check your answer. You can try. There's a, it's called percentile. You know, look up the documentation. 30%. I guess you can write it down if you want. Let me open up that page for us. I'll give you a minute. Try to write it down. Let's see if we all agree. All right. You can let Python do the heavy lifting for you, which is nice. Was that enough time to think of something? What do we think? Or one of us is thinking 12, though. Do we agree? Number that's at least as large as 30% of these numbers here. Are they already sorted? Yes, I think so. Yeah, let me do it with you. So let's see here. We've got these numbers, and 30th percentile of them. How many numbers do we have? Ooh, some of us disagree. Is it 14, perhaps? We'll figure this out together. Nice, but thank you for writing in your answer there. All right, we've got, well, n for us is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, I hope. Yes. And, all right, I want the 30th percentile. So I want 30 out of 100 times 9. That might actually not work out, will it? 3/10 of 9 doesn't really do anything for us, is it? So it's 30% of 9. So that'll give us the number, right? If there was one, go there. 30 out of 100, 3/10 times 9. Like if there was this number, I'd go to the 2.69 number. That would be where it was, but we don't have that number. We want the one that's the smallest number that's at least as large. So we'll go to number 3. Okay, so we want the third element, right? So it's it's like 2.7. So the 2.7th element, if I could get there. So that just means like go to round it up. So that becomes the third element. Does that make sense? Be the third element or the one at index 2. So 0, 1, 2, that would be our 30th percentile, 12. Questions about that? Does that make sense? And you can always confirm this. It's like, all right, if there's 9 numbers, 12 is the third of them, so it's at least as big as 3/9 of the numbers. That's 33%. That's very close. So it's really the 33rd percentile as well. But if we did number 2, if it was 11, it couldn't have been 11 because that's just as big as 2/9 of the numbers. That's only the 22nd percentile. Does that make sense to us? So we got to go to the first one that checks out that's at least as big. Okay, so that's how you calculate it. And yeah, let's do the rest just for fun together. The 45th percentile, the 89th percentile, just real quick. So the 45th percentile would be, this is the 30th percentile right there. So 30th percentile. The 45th, how could we calculate that? It's 45 out of 100 times 9. 4.05, so we got to go up to the next bigger one. We want the 5th element, so index 4. 0, 1, 2, 3, 4 is 15, so that's the 45th percentile. And the 89th percentile, That's all right. At least as large as 89% of these numbers. So 89, what number would that be? 89 out of 100 times 9. It would be the 8.01th number if there was one. We can't use the 8th number. That's not quite big enough, right? So we got to go to the 9th number. So that just happens to be this one. So 24 is the 89th percentile. It's also the 100th percentile, of course. But are there any questions about how we're calculating those things? We want the first number that's at least as large as p% of the values, 30% of the values, 45% of the values, 89% of the values. Does that make enough sense to us? That's something we care about, right? Those are some, like, how does it all relate? How does it stack? So there is a function legitimately called percentile, and I might as well show that to you. Okay, so it's called percentile. Percentile function in the data science library. It takes two things. It takes the percentile you want and then the sequence. All right, so we're going to call percentile in this way. We're going to say, we can give it a sequence, and we can ask for a percentile. Where was I? So we're going to be like, these are my numbers. Make array of all of them. And then you could ask for the, or let's just do it all at once. It's called percentile. You give it like 30 or whatever you want, and you give it the sequence, and it tells you the one. It's like, oh yeah, that was 12. Which is quite nice. Like, all right, the 89th percentile. Oh yeah, that was the last one. That was 24. So it's just, you say percentile, it's legitimately say the name, give the sequence. And so our documentation also should have that somewhere. Percentile. Hey, there it is. So you give it the percent, and then you give it an array that represents all the things that you care about. The array should be sorted though. Okay? Yeah, so you can use the percentile function to do this for you. Not horrible. All right, so you don't ever have to calculate yourself anymore. But that's kind of how that works. All right. If you are given numbers out of order, though, you do have to sort them. So let me show you how to do that. You got to say, like, if these are your numbers, make array 8, 6, 7, 5, 3, 0, 9. Our calculations don't make sense for this array, do they? Because they're all completely out of order. Like 0, the number 0 would be like the 1th percentile or something, the 1st percentile. But it's all the way over there. That would not be, like, the indices would be calculated incorrectly right now. So the way that you take an array and you sort it, one way to do it is you say np.sort. I don't know if I've shown you this before, but you just give it the thing and it sorts it in place. So this one actually changes the array. This changes nums. So one of the few functions that we have that change things for us. It also gives it back. So nums, oh no, I'm sorry. It gives it back. It does not change it. This does not change nums. Does not change nums. There is one that does, and I was thinking of that one. Sorry. So it gives back the other one, and nums is still, excuse me, unsorted. Alas. So you got to call it every time. You got to do it like this every time, or you could shove it right back into nums. So it would work out, and I think it should all be happy. Yeah. So think of it in terms of sorting, percentile, like 75 of np.sort nums. Should be all right. You know, now that I'm thinking about it, I don't remember seeing it, but you can always ask the question, like, what does it need? Percentile question mark. Does it need it sorted? When we're doing it, it wants it sorted, but it could probably sort it itself. Yeah, this one, in the example, of course, it's sorted. Let's see. It just takes an array, I think, actually. Yeah, so I think I may have remembered it incorrectly. It might be okay if we don't give it a sorted thing. It might be able to sort it for us. Percentile 75 nums. I haven't tried this yet. Oh, okay. In that case, we're good. Never mind. Excuse me. Yeah, you don't have to sort it. It'll sort it for you. So it's going to do everything. That's quite nice. So the 75th percentile is apparently 8. That's correct. The 25th percentile is going to be a small number, 3. Even though it's way over here, it sorts it. Nice. Nice. But if you ever want to do it manually, you can sort it with np.sort. Okay. That's so cool. I think that is most of what I wanted to say. So yeah, you can just give it to percentile. That's great. That's great news. Now we know. Any questions about this function? So it doesn't actually need it sorted. I didn't know that until now. I was looking at the examples from the documentation. Cool. So yeah, the percentile function is great. Are we ready for certain percentiles that we care a whole lot about? Because they're called quartiles. If you've taken a statistics class, you've heard of this before. But we really care about the 50th percentile a lot. You've heard that in math class already. That's called the median, isn't it? The median value is the number that's right in the middle. That is another name for that is the 50th percentile. That's quite nice. We also think of them in like quarters, cutting them into quarters. So you can also think about quartiles is the word. So the first quartile is the 25th percentile. It's the number that's at least as large as 25th of the numbers. Like with this example, it would be the number 3. It's right a quarter in the middle, right? If you can chop it up into 4s, the first quartile is that one. It's a number that's at least as big as 25 things, 25% of the things. That's the first quartile. The second quartile is the 50th percentile, also called the median. Then the third quartile is the 75th percentile. It's at least as big as 75% of the numbers. And these are slightly different. I will not ask you to do anything weird in this class about them because our functions don't really do it for us. But do you guys know that rule when you're calculating the median and it's an even length list of numbers? Like it's not quite the same. It's like the 50th percentile, if we ask the percentile function for these particular numbers, it would tell us that 8, I believe, is the, or actually maybe 7. Tell us that like 7 is the 50th percentile, one of the two at least. But really the median, if it's right in between, like there is no middle, you take the average of those two. The median should be like 7.5. You remember that rule? So I'm not going to ask you to do that ever, but people would disagree. The percentile function, if you ask for the 50th percentile of these numbers, is not going to give you back 7.5. So that is, there's that special rule where you have to deal with that. So yeah, you won't actually get the true median according to some people's definition of median when you use percentile. So that's interesting to think about. All right. So do watch out for that. I think that's all that I really wanted to say. So let me show you the difference. Like if you ask for percentile, the 50th percentile of this list of numbers. 1, 1, 3, 5, 7, 8, 10, 11, 11 again. That's okay if there's duplicates. And then 15. So yeah, it's going to be 7. That's the number that's at least as large as half of them. It is like the halfway marker. But really the median is 7.5 according to a lot of people. So there's a competing function for that kind of median. That's in the NumPy library. If you say np.median and then you give your sequence, that one's going to give you a different value. That one will do the 7.5, do the average of the two that were in the middle. Okay, so if you want that kind, you can say np.median. Otherwise, I'm not going to test you on the difference. Just you can use percentile 50 in this class. Is not going to make a huge difference in our answers. Okay, so I think that's what I wanted to say about that. Questions about quartiles? They're just special kinds of percentiles. All right, your turn. Try to calculate the first, second, and third quartiles of this list of numbers. And you can do it just in the simple way, I think would be the easiest. If you want to do it for the median, the fancy one, that's okay too. But try to give in some form, at least on paper. You don't have to do it. You don't have to post it anywhere, but just try it yourself. First, second, and third quartiles. Remember which percentiles those are, and calculate them. Even though you've got like an even length sequence, oh no, some things might go wrong. Yeah, I'll give you a couple minutes to try those. But those are important numbers. This is easy stuff to ask for on a test, so that's what we're practicing. And these numbers tell you a lot about the spread of your data. So, all right, what are the quartiles? Tell me. Even if you don't see a picture, get a picture of the whole amounts of data that you have. Like this still tells you, like, all right, how are they spread out? How much? Mm-hmm. I'll give you 30 more seconds as a head start. You can probably just use the functions if you want, because you will have those on a final. But hopefully you can also kind of see it. So like, where's the middle? It's about there, right? And another neat trick is like technically, the first quartile and the third quartile is once you cut it in half, take the median of that, there's your first quartile. Take the median of this, there's your the third quartile. That's a trick. That would be useful maybe. But all right, first quartile is second and third. What are these? Any brave soul want to say what the first quartile is, what they came up with? I think I selected it already. But do we agree? 4, 5, 6, 7, 8, 11. It's the 25th percentile. Dun, dun, dun. Oh, goodness. It is 5. Yeah, everybody agrees that it is 5. And a quick way to do it is like chop them in half and then get the median of the first half. That's how that can work. So for the same reason, 8 should be the third quartile. Does that make sense? That would be the 75th percentile. And then the middle, the midpoint, the 50th percentile is the median, right? That is 6 according to the percentile function. But if you want to do the fancy game of like getting the real middle, you got to take the average of the two true middle elements. It's either 6 or 6.5. Okay.
So I think the second one, either the exact one or they round it down. Like the exact 6.5 or they'll round it down to
not round it down, they'll do the average of the two middle elements. So this could have been, if this was like, I don't know, if these numbers were bigger, 99, 100, and this was 50, you would start averaging 6 and 50. Does that make sense? That's the alternative way of doing it. But yeah, you don't have to worry about that too much in this class. I will gladly accept this answer because that's what the percentile function gives you back. But the np.median function disagrees, and now you know why it might disagree. Okay? So yeah, I think that's all that I wanted to say about these. Other questions? That's a good question. Yeah, just go with whatever you know. I'll give you credit. I think that is my goal. And now I think we're ready for actually estimating things. I'm excited. So, all right. The age-old question. We're doing statistics, right? Secretly, with a computer for help. We want the value of a parameter. A parameter, remember, is something associated with our population. Like, I'd really like to know the average age of everyone in the United States right now. That's a very hard thing to calculate, right? Because people are being born, people are dying right now. It's unfortunate or great, depending on which side you're on. But that's what's happening. We have no clue, all right? Something like that. Or it's like something simpler. Like, what's the average age of the users who are going to like this TikTok that I'd like to advertise? All right? It's like you've seen sponsored TikToks probably. That's what you want. That's called a parameter. We don't know that. We'd really like to, though. We're going to have to do some stuff to estimate it, right? So if we had what's called a census is a sample of the entire population. If we really did know, if we showed that TikTok video to everybody on TikTok and counted how many people liked it, then we would have that number that we cared about. We could take all their ages, average them up, but that's completely infeasible and also not very useful if you're trying to promote it, right? You've already given it to everybody. You want to know ahead of time, like what ads to buy, essentially, like what age group to show it to. So you don't want to do that, okay? So you can't like give it to the whole population. That's usually infeasible. We can't go out to every household like go ask every human in the United States how old they are right now. That's impossible. Okay, so that's unfortunate, infeasible. So instead, we estimate. We estimate the parameter with a statistic. So a statistic is an estimate of our parameter. All right, that's the difference between those two words. They go hand in hand. The parameters on the whole population. The statistics is on our sample. All right. That's the goal. And so that's what we got to do. If we don't have a census, we can't calculate the thing exactly. We want to estimate it with a sample. We want to take a nice random sample if we can from the population so that we don't like sway too far in one direction. We want to get the truth if we can. And we'll use a statistic as an estimate of the parameter. Like if we want the average, we'll take the average of that sample. And that will usually give you a close enough approximation for most purposes of what you care about. You can take a bigger sample if you want precision, all right? So that's the name of the game with statistics. We're comfortable with that, yeah? Questions about that idea? Because that's what we're doing all day long. Okay. The next question, because that's what we've been dealing with, all right? We've been doing that already. So like this picture, I've shown it to you before. We got a population. We want to infer something about that population, but we can't like ask them all. So we take a little sample with some sampling method, usually randomness helps us get that, right? Perfect, nice random sample. We do some inference on that sample. We take the average of that, and that helps us infer the population's parameter, all right? With some degree of exactness. And we know that it's not perfectly exact, all right? Because if you take a sample of a certain group of people, maybe you overcounted the young people or something. You're skewed a little bit. So yeah, you could have taken a different sample is the question of this chapter. Right? This is chapter 13. So if you took one sample, that's just one estimate. You take the average of that sample, like you get an average age. How good is that? Like what if you took a different random sample of a bunch of different random people? It would be a different value, wouldn't it? It would be a completely different value. You could have sampled different people, gotten a different estimate. How much would it have changed is the question of this chapter. Like we want to know how much it varies. Variability is the technical term, which makes sense, right? How much does it change if I were to take a different sample, a bunch of different samples of the population of the same size and get that average age or something? Like how different would it really be? Because it should be approaching some true value of the population, some true parameter. How far away is it? How far away could it be? All right, so that's what this chapter cares about. Like, how different would that estimate be if I went out and got another sample, which a lot of the time that's impossible. It's costly, right? And then how accurate is the estimate that I'm getting right now with my one sample that I worked really hard on? Because I probably can't go get another one very easily. All right, so that's our question. And here is one way to figure it out. It's called bootstrap sampling. It's a cute little name, very American, I guess. So if we wanted to know that spread, like how different would it be? You need to go out and ask a bunch of people more things, right? You need to go get a bunch of samples. That's impossible most of the time, right? You need a bunch of random samples to get a bunch of different values of your average age. Like go ask 1,000 people a bunch of different times or something. That's hard to do, all right? We sometimes, like we spend a lot of money on this one sample. We cannot go get another one, all right? That's very hard. It's a question of time or money. Something a lot of the time you can't go get another sample. You have the one you've got and you need to know like how good is it, how different would it have been? All right, so that's the question we're trying to answer. All right, so if all that we have is that one sample that we worked really hard on, think about it. That one sample we tried to get a nice large random sample for that one good one that we spent all our money on. So in theory, that sample itself already resembles the population to some degree. All right, that was the whole point of taking a random sample. So here's the trick. It's very weird to want to do this, but it will work out. There is math associated with it that proves that it's okay to do this. If you take random samples of your original random sample, it will look like different samples of the population. Does that phrase make any sense at all? It's a weird idea to want to do that, but it's okay. All right, you got your original data. Here's the picture. You got all this data originally. You take a bunch, they're called bootstrap samples. Here's your original sample that you worked really hard on. If you take a bunch of samples of the same number of things, but this time with replacement, you'll get a bunch of different looking things. You'll like sample some things more times, less times. It will look like another kind of random sample from your population. And you can do that a bunch of times. And it's as if you're simulating more samples from your original population. You can help determine variability that way. It's a weird idea, but that's the trick. Are there any questions about that? So it's odd. It's odd to want to do that, but it would work. And here's kind of the picture. Question, yeah.
If you're using replacement, then wouldn't that skew your data?
In theory, yeah, I don't know. I am not a statistician. I was not trained in that, but there is some math associated with it that makes it okay. That's all I think I can successfully answer. But because sometimes like that, there may be more people like that one person that you sampled, I guess is the idea. Because you're sampling from a very large population where the people that you sampled are kind of indicative of a certain kind of person, and maybe you would have seen that person more often or less often if you took a different sample. I guess that's my hand wavy idea. Does that make a little bit of sense? Yeah. There is math behind it. Your book will maybe make it slightly more precise, but not super precise. That's for a future statistics class, like the real reason for why this works. But that's what you can do. Other questions? It's an odd idea. And here's kind of the law of averages is kind of the real answer, I guess, because we know that if we took a bunch of samples on average, it's going to approach something. It's going to approach the same idea. They're all going to look the same. So like, here's kind of what we want. We want a population histogram or something. We took a sample, we can take a histogram of that sample. In theory, it resembles our population. And then if we resample from this with replacement, we'll get a bunch of different kinds of new samples, and they're usually going to look very similar again to the true population because your sample initially looked similar to the true population. It's going to give you how many different ways it could have varied. All right, all the different ways that sample could have been maybe taken a little bit differently. So it's a cheap way to get a bunch of new ideas as to how your sample could have gone, if that makes sense. All right. And so if you take a lot of them, on average, it's going to approach something, and that thing is hopefully the truth. All right. If you got enough. If you got enough, it will approach what it should be in theory with a certain amount of variability, and we'll be able to quantify that. Okay. So that's the goal, and that is bootstrap sampling in a nutshell. So here's the process, all right? This is what happens. So with a high probability, according to math, if you were to resample from the original random sample that you took, it's as if you were sampling again from the population. So maybe you found that same person a couple times or similar people a couple times. It's okay to double count them when you use replacement because of that, because there might be more people that look like that in the population, or less if you don't count them as many times with that value. So that's okay. So as long as you take the same amount, all right? It only usually works when the original random sample was huge. As big as humanly possible is the best idea here, because that means that your sample is pretty close to the population. You took a decently large sample, then it really does reflect the population well. So you do have to be careful about that. You can't like take a sample of 25 people and use that and resample that and think about the entire population of the US. So like you need a decent sized sample still. But if you do it, if you have a decent sized sample and you resample from that sample, that's as if you got another sample from your population. That's the goal. Mathematically, you can prove that. All right. So here's the bootstrap process. What you do is you take another sample at random, you random sample from your sample, randomly with replacement, just as many things as your original sample had. So if you're asking 1,000 people, you get another 1,000 size sample, this time with replacement. You double count or don't count some people in that original sample, and that will help show you how your random sample could have varied. Okay? So it has to be the same size so that you can compare. You can't like take a 2,000 size sample out of a 1,000 size sample. That's impossible. That doesn't make sense to do that. But that's the trick. You pull yourself up by your bootstrap. That one. All right. So yeah, let me show that to you, and that's the process. And let me show you how that works and how it kind of helps estimate things. I can prove that it works. I can't teach you the actual math because I'm not super trained in it, but I can prove to you that it's going to do the right thing. All right. So bootstrapping. Whee! Here we go. So I'm going to import the following file. It's going to be a file about salaries in San Francisco. So it's this data San Francisco 2019.csv file that we're going to include right now. So that's actually that's actually a census. It's kind of nice. Population. Let me show it to you. Equals table dot read table data / San Francisco 2019.csv. This is our pie in the sky dream. We have about 50,000 rows, and one row is one. I think it's just a bunch of public employees from San Francisco, like who worked for the city, which is kind of neat. So they're in a bunch of different places. Here we can do like a sample of them. Give me 10 of them, please. So here's how they look. They've got like where they're from, their department, a lot of different stuff associated with their job. Each row is a person in a job who works for San Francisco in 2019. Here's their salary. Here's how much overtime they got, their benefits, and then their total compensation is that. All right, so you got it all over the end of the spectrum. Like maybe this person was definitely a part-time person or something. But you got all these different values, and this was every single person who worked for San Francisco in 2019. So this is actually a census. This is a population, all right? We're going to take a sample from this and show that it ends up being similar to the population, right? So it is almost never possible to get data that looks like this. We were very thankful. I can use it to prove something to you right now, but you almost never get this. It's almost never possible to have the entire population, but we're going to practice with one. So I can show this to you. Show you that bootstrapping works. All we usually get are samples, all right? So what we kind of care about is going to be, let's focus on the total compensation of all the people who worked for the city of San Francisco, all right, in 2019. So it's the total compensation field label here. And so let's take a look at that. We can do some histograms, we can do some sorting. So here's our population. This is every single person who worked for San Francisco in 2019. Sort by total compensation, and we'll do descend. Oh, let's do it to start like this. There are some weird like filler things. I forget what your book was saying. I'll have to go back to it. But either these were total compensation is 0 for a certain amounts of jobs here, and that's interesting in itself. These could have just been like people doing multiple jobs. I forget what your book said. I'll have to go back. It's like either somebody also had this job on top of their other one, and like this didn't add to their salary, or this was like an open job that was not filled yet, something like that. And so these are like, there's a bunch of people with total compensation 0 right now that we shouldn't probably be considering. If we do descending equals true, you can see the highest paid people in San Francisco, the public employees at least. And so it looks like the person doing the retirement services, the chief investment officer, had a lot of money at the end of 2019. Good for them. All right. And that's like the highest salary. And then it just goes down from there. Nobody else was making over $700,000. Must be nice. So yeah, that's what that looks like. And we can take a histogram of the total compensation. All right. So we can say population dot histogram on the total compensation. And we can ask it to do a bunch of, like, its default bins are probably not enough. It looks weird. We can say bins equals like 20 or something. That's probably decent. But what your book does is they kind of cut it off at about 600,000 because like that's the last one where there's multiple people. So that's the bins that your book likes here. Bins equals np to a range 0, 600,000, going by increments of 25,000. Those are the bins that it cares about. So that's the picture that we can draw. So there's a lot of people that are making not a lot of money, but it was those filler jobs with like zero amounts of money. So we kind of want to get rid of those because those don't really tell us much. It's like there's not that many people making no money who work for San Francisco. Those were like filler posts, job posts, or people were doing some other job as well, something like that. All right. So let's get rid of all the people who made like less than a part-time wage. I think would be nice. That would give us a better picture. All right. And again, this is a population data. Like we don't usually get this. What would happen if we, like, our goal I want to show you is like, what happens if we asked 1,000 San Francisco employees what their total compensation was? How close would it look like to this? That's our goal right now. All right, that's where I'm going with this. So let's, because of this total compensation 0, it's making this spike appear here. Let's get rid of that spike by just considering people who make more money than a part-time wage. So here's like the minimum salary that we care about. Let's do, I believe, if I remember correctly, it was $15 an hour in 2019 was like the minimum wage in San Francisco. And if you're a part-time worker, that's 20 hours a week. And let's say there's 52 weeks in a year. Let's say you got 2 weeks of vacation, so 50. Let's say that is our minimum salary that we want to care about. Everybody below that, like we can disregard. So that's like $15,000 a year. So let's say, because minimum wage was $15 an hour, $50. They're part-time workers, so 20 hours a week and 2 weeks of vacation, let's say, unpaid. There we go. That's the minimum salary we'll care about. And so let's change our population table into that. So we'll be like population where the, let's do the salary at least. Salary was above that, and then that will affect the total compensation because that's part of this. Salary is part of that, a big part of it. So where the salary values are above, let's say, above or equal to that min salary. Something like that. And let's set that back into our population. All right. So now all of our salaries are like non-zero. Okay, and let's deal with those people now. All right, and so let's get a histogram, one last histogram of everyone with the bins in the same way. And now you see there's not a spike around 0 anymore. That looks more accurate. So a decent number of people were making over $100,000 because San Francisco is a very expensive place to live and they have high salaries there. All right, so that's our graph. This is a graph of our population. Like this is everybody who is working a public job for the city of San Francisco. That's something we don't usually get. All right, and we can ask for, like, maybe we care about the median value of the total compensation for these people. All right, so we can ask that. We can say percentile, can't we? Percentile of the 50th percentile of the total compensation, and that's just a column. I can get that array by taking this column, right? I can turn it into an array by saying, please population dot column total compensation. And we know we don't have to sort it, which is great now. And that's going to be our population median. That's the median salary for public workers in San Francisco. All right, population median. We don't get that number usually. All right, so this is like a dream right now, population median. You could also have used, remember, you could also use np.median. np.median works too. It's another function that does just the median. Percentile gives you every percentile that you ask for. We could also say np.median of this. And let's see if it's an even number. Let's see if there's a difference. np.median. No, it's the same. So there was an odd number of people, or there are a bunch of duplicates of that salary or something in the middle, or something like that. So either way would have been fine, but like that's the compensation data and the histogram and the median of everyone. All right, that's the true median for public workers in San Francisco. Does that make sense so far? That's what we started with. And now the question is, because usually, I'm going to show you something. Usually, you don't get this. You don't get this data. You are asking, maybe you can ask like 1,000 people, 1,000 public workers, what their total compensation is. And the question is, how close do we get when we take that sample? We take the median of the sample, right? This is the median of everyone. We're not usually going to get that. Let's say that we asked a few hundred people what their total compensation was, and let's see how closely it resembles this histogram and how closely the median resembles this number. Because like this is the true value. Like this was our dream. Pretend we couldn't get that, and we had to use random sampling. I'm going to show you how that bootstrapping is going to work. All right. So does the game make sense that I'm about to play with this data? We're going to pretend that we took a random sample of, let's say, 400 people. Let's pretend we took a sample of 400 people, and that's all we get. So we went out on the street, or outside of the public building in San Francisco where they all work or something. We asked them their total compensation, and that's all we get. So that's our sample size. All right. So I'm going to show you that this is all going to work out. All right, everything we've been talking about. The bootstrap process will do the thing. All right, so our sample size is 400. You can change this later if you download this. So we're going to take a bootstrap of it. We're going to take just a single sample right now, and I'll show you what that is. All right. So our sample is from the population. Please sample as many people are as in sample size, and I want with replacement. That is the default, but just to drive it home, with replacement equals. Oh, I'm sorry. No. This time, this is our original sample. We're going to not do it with replacement. The bootstraps we will do with replacement. But this one's not with replacement. We're just drawing 400 actual people. We're not duplicating any of them. All right, so this is like you're asking 400 separate people right now. All right, so 400 separate people. No replacement, no duplicates. All right, so that's going to be my sample. And we can do a histogram of that, of course. That's a sample.histogram. And now the question is, how closely does it resemble? Sample.histogram. So does what I'm about to do make sense? Like I'm about to get a 400 size sample from our population, 400 separate people. It's as if I went and asked them what their salary was. And that's all I have. And I'm going to take a histogram of that. And we're going to see like how closely it resembled the real histogram. This is the true one that we wish to have. We don't usually get that. Does that idea make sense? That's where we're going. And here it is. Look at it. If I scroll really fast, do you see that it's kind of similar? It's very, very similar on the ends, at the start, like goes up and down. There's like this jump right here is a little bit bigger than this jump right here, the true one, the true values. But that is decently approximating it, right? And so we can take our sample and see like what was the median. So the real median salary is 135,000-ish per year. We can get the 50th percentile of our sample total compensation. Sample.column total compensation. And do you see how it was 131,000 rather than 135,000? It's decently close, but not quite the same. All right. So it's as if we got this value, and we want to infer, like, all right, how good of a value was that? Does that make sense to us? So like we wanted the real value. We know that the real value is secretly 135,000-ish. We got about 131,000. And that's all you usually get. It's like, all right, how good of an estimate was that is now the question for us, okay? Because if we took a different sample, here, let me just quickly take another sample. Oh gosh, do I want to replace this one? I don't want to. Let's do it again. We'll do like sample 2.histogram, sample 2's percentile column. So if I do it again, this time I got a different value. If I do it another time, this time I got a different value. It's around 130,000. This one, 133,000. So if I keep doing it, I get different values. Does that make sense? Get different values for my samples. And usually you can only run one sample. So like you didn't even get this one, all right? Usually you can't even do this. You can't get another sample like this. And so what we got is like we got our one sample called sample. We can bootstrap it, all right? That's our goal. Let's get another, let's do a bootstrap process where we take as many people as we sample, so 400 people. We draw 400 of them with replacement this time. We sample from our original sample with replacement randomly, and we see what the median was then. So like this was our original median. This was our sample median, right? Our original sample median. Let's see how it compares, okay? So I'm going to do a bootstrap now. I've got my sample. I've got my original sample, and I'm going to sample it, right? And remember what you do when you sample. You got to say how many things you want. Let's see here. Where are we? There it is. You got to say how many things you want. That's your K value. It's how many things you want. By default, if you don't give anything, it's just as many as there were. And then by default, also, it's with replacement equals true. So if you want to fill it out, it's like I want just as many things as were in my original sample, so 400. So it's the same as sample.numRows, same amount. And I want with replacement equals true this time. I want to duplicate people because maybe there were more people like that in the real population. So I could have just said nothing actually to sample and it would have worked, all right? So sample dot sample without anything at all would work here, because the defaults give you what you want. So there's my my bootstrap sample. Bootstrap sample. I'll call it that. And then, or I could call it, I guess I am resampling as well. So I could call it resample. It's my resample. Shorter that way. And then I want to take the 50th percentile. Well, let's actually look at it first. So if I take a resample, it looks like this. Sometimes there's duplicates. It's just another table, right? It's another table of 400 values. It changes every time. Who's in there? I can get that column of it, right? Dot column of total compensation. And it's a different value, different 400 values every time, right? And they're in different orders because it's random. Sometimes there's duplicates, sometimes there's not. I can ask for the 50th percentile of that. And here is a bootstrapped new sample, right? So our original sample's median compensation was this, about 131,000. We got a similar value for our resample, all right? If I run it again, ooh, I got 135,000 this time. Do you see how that's like giving me another value? That's actually, that one was really, really close to the true median, wasn't it? That's cool. And so if I keep rerunning this, I'll get a bunch of resamples, and the goal is to do it a bunch of times to see how it might vary. It's like this is me pretending to take another sample. And if I do this enough times, it really will approximate the true thing. All right? It really will approximate the true thing. It's great. Okay? So I want to do this essentially in a function. So let's take this and put it into a function. It's like I want to get back, please, one bootstrapped median. Bootstrap median. So, boop, just like this. So this is and then I return this. So what I'm going to do is, the very first one is like draw the bootstrap sample, take the sample, and then I want the median total compensation of that resampled thing. Return the median total compensation in that bootstrap sample. And it's different every time, just like I showed you here. It's just running that code a bunch of times. And now that I've got this, let's do that. Let's do like 1,000 resamples and see how it varies. Because this is us pretending to take another sample from the population. It's good enough, all right? It'll help us show how much it varies. So, all right, let's make an array, a blank array of bootstrapped sample medians. Empty array. So this is stuff we've been doing for the past 2 chapters. Let's say that I want to resample 1,000 times, and then I'm just going to loop for I in np.arange num resamples. We can change that more or less, but 1,000 is a good amount. So I'm going to get I'm going to get a bootstrapped median, right? So like a new median value when I call my get me a one bootstrap median function. I want to add that to my list of sample medians. So I'll say np.append bootstrap sample medians. Remember, if you type tab, it'll try to autocomplete for you, which is great. Give me my new median, put it there, and add that in to bootstrapped sample medians, please. And so once this is done, I'm going to have 1,000 resamples of my original size 400 sample that looked like this. It wasn't quite the same as the original population's histogram, which was this. But because it's big enough, if I resample from it, it's as if I got more samples from the original population, and I can do a histogram of, I can see where the medians lie now. Okay? So let me show that too. Let's put all these medians, these are like bootstrap sample medians. Let's put all those in a table. So like give me a table, a blank table, with a new column called, bootstrap sample median. Is that. Those are their values. So here they all are. See, sometimes they're very close to the original, like 135. That's the true value. We didn't know that. But sometimes we get that. Sometimes it's smaller. So it's as if we took another sample from the population. It's a very cheap way to do that. It's quite nice. So let's do that. Let's make this table. Bootstrapped median table, I guess, is that. And let's do a histogram. Bootstrapped. Give me a histogram with like, I don't know, 15 bins. And this is not the same as this histogram. Remember, that was total compensation. This is like the medians that I have sampled and generated. Remember that the true median for the population, the one that I really cared about and was trying to estimate, was 135-ish thousand. I can add that to this graph. So let me do that real quick. So don't worry about what I'm doing. I need to change the y limit. I don't know why I'm doing that. That's a thing. And then, oh wait, it has to be super small. Never mind. 4 of those. Because of the y-axis there, it's disgustingly small. So 1, 4, there we go. Scatter. So I'm gonna add the population median as a little dot. You don't have to understand. S equals 40. Why did I use double quotes for that? I do not know. There was no need. So there is our true value. And do you see how our original sample was not that value? Our original sample's median total compensation was 131-ish thousand. It was down here. But when I took a bunch of resamples, I eventually got some that had the true value in them. And so this is kind of the range of the values that I saw when I took that resample. And they're about between 125-ish thousand and 145-ish thousand. Do you see how the true one, when we did that resampling process, the true value for the median compensation appeared? Are there any questions about that? It happened to appear, and so this is as if we took a bunch of different samples, and it's telling us how that median could have varied. And do you see how we actually found the true value in between some of the values that we generated? That's the secret here. That's what we care about. That's what we want, all right? And so all these different resampled medians, they're great. Let's see. All these different resampled medians, yes, wonderful. We get a bunch of values here. But we found the true one is secretly in there. And usually we don't have this dot. We have no clue what it really was. But when we take a resample and we do this bootstrap process, we get a range of values that it could have been, rather than just one from our original sample. And that range tells us how much it maybe could have varied. And that's going to give us more of the truth, like where that value really could have been. Because usually you're not going to have this stuff. You're like, all right, I got this value for my own sample, but how could it have ranged if I took a different sample? All right, because you're trying to approach the true knowledge of things, which you don't have. At best, you can give back a range of where it could be. Does that make sense to us? Question, yeah.
So are we looking for more like a range, or do we want our samples to be closer to that random?
Oh, you're never going to get it perfect. That's the whole point of sampling. Like, you're never going to have this true value, but you want to know, usually it's the range. Like, I would like to know, like, the range of values that this true value could be in. And that's what we just generated. We generated that range. Yeah, we care about the range now. If you wanted a tighter range, do you see how all the values are between like 125 and 145,000? Yeah. Like, that's a good answer. Like, that says that most of the time it's going to be that. That's probably where the true value is. If you wanted a tighter range, like between a couple thousand only, you would have had to take a bigger sample, not just 400, maybe like 1,000 or something. And I highly encourage you guys to play around with like, that range is going to shrink if your sample was bigger. I hope you can imagine that would happen. All right, that's kind of intuitive, I hope. But yeah, that's really, really cool what just happened. Any other questions? That's a good one about what we've just generated. So pretend that red dot wasn't there. Our goal is like to estimate the range in which the true value lied, and the bootstrap process gave us that. That's what we were getting. Because our one sample, we know now that's not good enough. Like that, it's not quite the real value. It's not quite the real value. But the question is, how could it have varied? Where is that real value? That's the purpose of this chapter, right? And one way to discover that range is like this, all right? And so that leads to a very, very important concept, and I think this is where I want to stop. I'll let you try this in a second, but that leads to confidence intervals. Yes.
Just to kind of like do a little understanding, why would you want to know the range of where the true value is when you can find the true value?
Again, yeah, that's exactly the point of this. We are almost never going to get this true value. We were just really lucky that San Francisco published this data. Pretend the whole point of this example is that I can prove to you that bootstrapping works. Pretend we didn't get this data and we just got this. We asked 400 people on the street who work for San Francisco, what is their salary? Our goal is to figure out, using that sample, what was the true median salary. Does that make sense?
So you move backwards, basically.
Yeah, exactly. So we pretend we never had this to begin with. You all will almost never have it, but I'm showing you that if you, even if you didn't, you could approximate and approach the real value with just a sample. Yeah, we are lucky to have that as an example, I would say. But yeah, it's just like pretend we didn't have it. We know what the real value is right now, just for the sake of example. But pretend we didn't. How could we discover the range in which it lies? Does that make sense? Yeah, that's a great question. All right. Other questions before I get to the idea of a confidence interval, because that's the real name for that range. That's the real name for that range. By doing these resamplings, we get a bunch of different values for that median and see where it could have been, and we can kind of like take a percentile all over again, but it's like a middle percentile if you think about it this way. So the idea of a confidence interval is that we pick a number like 90%, and we can give back a range of values and say that we are 90% confident that the value of the true median salary lies between this number and this number. That's something we can generate now with these resamples and what we've got so far. And you're able to control the percentage and also use it as a p-value. I'll show you that in a second. But that's the goal. All right. You can control that percentage if you want, because what we've done, right, is we've gotten a bunch of random median values for where the total compensation will lie. If you want to give back a number that is 90% accurate, you just give back a range that contains 90% of your sample median, of your simulated medians. Does that make a little bit of sense? It's like cut it off at, like, this is 5%, go up to 95%, like take those two values, give me the 5th percentile, give me the 95th percentile of those median values that I've generated. That's your lower end and upper end. 90% of the values lie within that we've generated. 90% of the values that we've generated lie within that range now. And so you can say that, all right, I am now, if I give you that range, I'm 90% confident, given my simulation, that the true value lies within there. That's what you can do. So that's kind of neat. So usually 95% is what people care a lot about, because like 5% is a huge cutoff in statistics land. They care about that. So if we got all these estimates, right? The middle 95% of our estimates gives us an estimate that's correct 95% of the time. We're doing this simulation, this random generation. It says if I took 1,000 different samples, how many of those samples had this value, had this value? That's what we're doing. All right. So the middle 95% of your estimates, of course, if you take more, it's more accurate, are going to be correct 95% of the time. Like you're cutting off 5%. And you're pretending that never happened, right? So you're going to be 5% of the time wrong in that case, but 95 is a good number. And that's called a confidence interval, all right? So let's calculate the 95% confidence interval for the median salary given our sample and our bootstrap sampling process. That's one way to do it. So I'm going to take where is it? Here are all my samples, my bootstrap median samples. Bootstrap sample medians. I'm going to take percentiles of those now. So the 95th percentile, the 95% confidence interval is going to be the range between, we want the middle 95%, so it's going to be the 2.5% percentile all the way to the 97.5% percentile. Does that make sense? Like that would be the middle 95% if you subtract the two. All right, it's the range we want here. That would give us the middle 95%. Okay, so I want the percentile, the 2.5th percentile of this one, and then I also want the 95th percentile. And if I put a comma between them, it'll show them both to me on the same line, which is what I want anyway. 97.5. All right, there is my range of values. And so all this process, taking these 1,000 random bootstrap samples, getting all the different ways that the median could have been, and seeing how often we saw those medians, leads us to this now. So give me the middle 95% of values that I have simulated and generated. Here they all are. We can say that we are now 95% confident that the true value of the median salary is between 127-ish thousand and 141-ish thousand dollars. Does that idea make sense to us? It's an interesting idea, and we know that our answer is within there. We did it right. Like, it is going to work. But usually you don't actually know that true value. You don't know that red dot. But we have successfully, from our sample, our pretend sample, figured out that yes, it is within that range. All right. And so hopefully that gives you confidence that confidence intervals work and this bootstrap process works. That's what I'm trying to tell you right now. All right. Any questions about that? You could also have made like a 90%. What is it? A 90% confidence interval by taking the values between, what would that have been? Between 5% and 95%. This would be a 90% confidence interval. Huh. These would be these ranges. We can say that we are 90% confident that the median salary is within these two values. And we know that we got lucky this time, and it really is, but 10% of the time we are going to be wrong. That's the whole point of saying we're that much percent confident. All right? 10% of the time it actually won't be within that range. So that's why you want to keep your confidence interval as wide as possible. But when it is this wide, with a higher number, with a higher confidence number, it's going to be a wider range because you have to be more careful. That's what's happening. All right. So yeah, that's a 90% confidence interval. And yeah, I have all this data for us. I think we have a few minutes left. How about you guys try this? So we did this for the median values. How about I have you try this for the average total compensation values? Because it would work exactly the same. So let's do that. So here, we got our population. That's our, it's just called population. We can get the population mean. Let's do that. And I'll give you a head start. And you guys can tell me where to go if you want to like copy stuff down if you haven't gotten it yet. But let's do population mean is np dot, I guess we can just do dot mean, right? This is the value we don't actually know. The mean total compensation is this. All right. The mean total compensation is this. We would like to let's do a sample, right? Using bootstrap sampling. That's my crushed ice for you. Using bootstrap sampling, calculate a 95% confidence interval using a bootstrap sampling and another, or just use the original and our size 400 sample. Calculate a 95% confidence interval for the average salary, for the average total compensation. So it's pretty much do everything that we did, but instead this time do averages rather than medians. Does that idea make sense? So I'd like you to try that if you can. What is the easiest way for me to give you this code? That's my question for you now. I doubt we typed it all down. So let's see. This is probably where you want to be. This was us taking a sample. That's important stuff. Here, I can put it all on Discord, I guess. That could work. That would work. Or actually here, an easier one would be let me put all of this code right now on our code from class, which I have put on Discord. I'll give you like 7-minute head start and then I'll do it for you. Let's see here. We've got if you now go to and by now I mean now, if you go to our code from class, this one right here, this last link that I put on our Discord, you now have our chapter from today's stuff. It's chapter 13, and there's everything that I've typed so far. You want the bottom, but I think that should be what you need. All right, so I'll give you a few minutes and I'll come around and help. Try to use this process with another size for, take another sample or use the original one if you just want to rerun this file. Calculate a 95% confidence interval for the average compensation, not the median compensation anymore. All right. Or if you don't want to do average, you like the 25th percentile compensation, the 75th percentile compensation. Something like that. But I'll give you like a few minutes head start and then I'll do it with you. All right, but you have the data now. It's in that last link on Discord, as well as the data file is there too. That's our San Francisco 2019.csv file. Yeah, are there any questions about what I'm asking? So you're going to get another sample. You're going to make another function that's like one bootstrap average this time. To do a resampling of just as many values with replacements. That's you simulating another sample of your population nicely, using the bootstrap process. Do it 1,000 times. Get 1,000 averages from those resampled samples. And then you want to calculate, all right, using all those values that I got from those resamples, what does the range look like of values that I have generated using that? Because that will tell you something about what the true average compensation is, which we know to be this, but let's pretend we didn't know that and see, just prove to ourselves that this process works. So just like pretend we didn't get the population mean, because that's what we're always trying to approximate, usually with a range, with a confidence interval. This is exciting. Nice to have the true data to prove to ourselves that this process works. We almost never get this true data. We'll point in this idea of bootstrap. Methods. Let's calculate a range that we're comfortable the value might be. All right, that's my time to give you a head start. So you can keep working if you want. Don't stop listening to me. But I'm gonna try it too. And so I'll just use the sample that I've already took, the one that we did the other one with. So I've called that sample. You can also use sample too. So here's my sample. I took a sample of the population. Let's pretend that's all I have to work with. What's the mean of the compensation for that sample? Whee! It's a little bit smaller than the true one, but that's what we got, and we're not sure how good of an estimate that is, because this is always hidden to us, that original one. It's really just hidden to us. Okay, how good of an estimate was this? How could it vary? And so that's what a bootstrap sample does for us. That process lets us try a bunch of different values. Let's just get back a bunch of different values that we could have received from our sample, right? We're pretending that we got more samples and seeing how the values could vary. So yeah, let's make instead of a one bootstrap median function, let's do a one bootstrap average function, or mean. I'll do average just so that it doesn't look the same. So we get another bootstrap sample of the same amount of rows and size and things. By default, with replacement true is there, and by default, it's as many rows as there was. So I can just say sample.sample, which is kind of cute. And then I want not the 50th percentile, I don't want the median anymore, I want the average total compensation in that new bootstrap sample. So one way to do it is say dot mean. You could also have done like np dot average of that column. A bunch of different ways to do it. Well, we can do it that way this time. Why not? np dot average of all those things, please. And so every time I call it one bootstrap average, I get another estimate of that. Sometimes it's smaller than the sample's estimate. I'm sure it will also sometimes be bigger if I ran it. There it goes, another few times. And the true value is this, 143-ish thousand, that we don't get to see, right? We don't have that. But we can estimate, we can see by taking a bunch of bootstrap samples and seeing how they all compare. All right. So I'll make another loop here. 1,000 times, this seems fine. We'll do sample averages this time. Averages. Boop, boop, boop. And we'll call it still 1,000 resamples. We'll do a new average. New bootstrap average. Boop. So we've got that one, and we'll add the new average to it. And I believe I've done this right. Let's run it. It's going to do it 1,000 times, the resampling process, bootstrap sampling. And I got a bunch of values in this bootstrap sample averages table that I could arrange in a histogram. So let's just quickly do that. It's not bootstrap sample median anymore, it's average. Bootstrap sample averages. And it looks like this, but I can take a histogram. I don't know, with 20 bins or something. And here are the values. It looks like the values that we've generated, they do contain the true value, right? Our original sample had this small value of the mean compensation, 137,000. That's what it's going to center around, of course, because that's where the sample was. But when we do the bootstrap process, it will eventually, usually a certain amount of time, also get towards the true value on the other ends, because that is possible, right? That should have been in a sample eventually. So if our sample is random and good enough, we should be able to see this through the bootstrap process, 143-ish thousand. And it's over here somewhere. It's part of the sample. That's good. It's part of the bootstrap samples. That's great. So let us find that. Let's do a 95% confidence interval of where the average compensation value is. In the same way, it's going to be, again, 2.5 to 97.5. You want the middle 95%. And it's of the averages this time. And so this process, the 2.5 percentile, the 97.5 percentile, between those ranges, there's 95% of our data, of our generated averages, and we're missing 5%. So we might be wrong 5% of the time, but we are saying that we are 95% confident that the true total compensation value is between this range and this range. And did we get it? 142,000, 142,675 142,984. It is within there. It's on the edge though. So this maybe was a sample that took some low paid people. You also have like some very average is harder as well because you got those very like that one person that made $700,000 that was driving the average up. And like if you didn't sample that one person, now you're a bit off. But we are still it's still within our range, our 95% confidence interval. You better believe that if we took a 90% confidence interval of this, we would actually not have the true value in it, right? It would be a little bit too small on this end. And so we would be within the 10% amount of time that we were wrong. So that is something to think about. But yeah, we are confident that it's within this range 95% of the time, and because we just so happen to know the truth for today's example, we can see that the process does work. Okay, and so that's what I wanted to say. I would say median is more likely to be correctly generated than average because of those extreme values that can bring it up or down, but it's still going to work out. All right, so I think that's what I wanted to say. Are there any questions about this process? Do you see it? It's a very neat idea. Helps you get a sample from, let's say you make arbitrarily many samples from just one sample that you got and you worked really hard on, and it's really expensive to get another. So that is great. We will come back next time and talk about how to use this as a p-value, like to do a statistical test using a confidence interval, because like you do have it's very similar to one I think you can see. And then I'll just have you try a bunch of examples and we'll practice. But I think that's what I wanted to say. Are there any questions about any of this? Bootstrap sampling is very fun and interesting. We made a bunch of resamples. We noticed that helped us get a range. All right, if we are happy, do remember that I've posted all of your assignments for the week, as well as Project 2, which I've released on our Discord, because Canvas is down. Let's refresh the page one last time and see how it's doing. No way. Moment of truth. Are we back in business, guys? Let's see. Oh, yeah. All right. So, yeah, I can do everything normally now, it looks like. Project 2. There you go. Nice. So, good for us having a late in the day class. But I think that's all that I wanted to say and have recorded. So I'll stop the recording.